Thanks, Nicole. Hey, everybody. Welcome back, or welcome to a new session here. I'm excited to introduce Dr. Troy Peters. He's a professor from WSU Extension in Prosser, and he's an irrigation specialist at WSU Prosser. He is located, reading my own notes here. He has been there for 15 years. He's also a licensed professional ag engineer and a certified agricultural irrigation specialist. Please welcome Troy to discuss new technologies in irrigation. Take it away, Troy.
Great. I hope everyone can hear me, right?
Yeah, we can hear you, see you, and see your screen. You got the trifecta going. Yeah. Thanks, Troy.
So to answer the earlier question about the Tier 2 stations, I'm pretty sure that they can. So when Dr. Brown took over the management of AgWeatherNet, he took some stations that he kind of separated them into different tiers, and stations that were originally there, and then he kind of made a Tier 2 station. Those ones are still there, I'm positive. And as they add new stations, those stations should be available on the Irrigation Scheduler mobile app. So anyway, so what I wanted to talk today is kind of like the big picture of irrigation technology comparisons. Basically, which ones are better than others, what different technologies we should be looking at, and which ones are kind of, yeah, you can save water with them, but the cost is so high that, we should just ignore them for now. So with that, I wanted to talk about kind of the big picture as to what is conservation, looking at the overall water balance to a drainage or to an area. So we have precipitation, how we can get water in, of course, as we get precipitation in, and then we have surface water that flows in. This is a graph that I did for the state of Utah, so you can see here. But then, and then we have water leaving the basin as a whole as either runoff, surface water out, and then this evaporation or wind drift and evaporation. Basically, it gets converted to water vapor, and then it blows away, and then it's gone. So we can do this soil water balance this way. So the timing of the surface water out is pretty important, because if we're trying to use that water, there's times when there's not very much water available, and then there's times when there's plenty of water available. And usually the times when there's least amount of water available in the surface water runoff is when there's the greatest shortages of water and greatest need for water for irrigation. And then we have this change in the storage. So we can change, we can store water in the basin as a whole, either in a reservoir, or we can store it in the soil. And so we can lose water to that storage from runoff or to deep percolation. So deep percolation is that's water lost out of the bottom of the profile. So the water losses, if we're thinking about irrigation, the water losses to runoff off of the bottom of the bottom of the field, it runs off and then goes into a ditch somewhere. Part of those can be recovered and part of them can't be. Deep percolation is the same. Part of that can be recovered and then part of it can't be. However, these evaporative losses, once it gets converted to water vapor and then blows away, that is pretty much permanent water losses, and you really can't count on ever recovering those water losses. So if we think about irrigation efficiency in those terms, what we're trying to do with irrigation is to store water in this root zone right here. So we can put water onto the soil, and then the water goes here, And then if we apply different amounts of water in different areas of the soil, we have to, there's water losses to deep percolation. Whenever we apply more water to the soil than it can hold, that water goes out the bottom of the profile and that water is lost. Or we have the runoff water here. So this is what I was talking about, runoff and this deep percolation water losses. Deep percolation goes into the soil, it comes out in a spring somewhere, or it recharges the aquifer. Some cases we can recover all of that water. Some cases we can recover none of it eventually. But for the irrigator himself, that water is lost to him, at least temporarily, but may not be lost to the state. Whereas these water losses from the spray, as the sprinkler operates, we lose water to wind drift and evaporation. Those losses are permanent. The evaporation of irrigation water from the wet leaves of a canopy is permanent. Water loss of evaporation from the soil surface is also permanent. So anything that's evaporation, these spray losses, these are not helping us. These are not getting us what we want. That's not really a great thing for irrigation. What we want is we want transpiration. And transpiration is water that's actually used by the crop, and that water is lost out of the leaves of the crop. So that's what we're going for. And transpiration is usually pretty linearly related to the overall yield. So the more transpiration we get, the more yield we can get. But again, at some point, transpiration is limited by other things like sunlight, etc. So to talk about the uniformity of that irrigation system, it's pretty important, right? Because if we look at this, if we have poor uniformity, our system cannot be efficient if it is not uniform. It's just not possible. So we can, a common way of measuring uniformity is we put catch cans out and we measure how much water is caught in each of these different catch cans as the system operates. This is for a center pivot, but you can do it for any type of sprinkle irrigation system. Doing it for drip irrigation, basically you lift the drip tape up and you measure the flow rate coming out of each individual drip emitter. Surface irrigation is much more complicated. But what we're trying to do is we're saying, okay, if we take all of the catches, the depth of water caught in each can, and then we sort them from smallest to largest, and then we take the overall average of all of these catches in that particular field that we did the evaluation for. And then we take the low quarter, we take that low quarter and we divide it by this overall average to get what we call the distribution uniformity. And why this is an important number is because, let's say we want to apply 1 inch of water to the whole field. We've watched evapotranspiration. The crop has used 1 inch of water everywhere. Well, in order for us to put 1 inch of water everywhere with this particular system, we've got to over apply water everywhere in order to adequately irrigate this low quarter. And so that's what we do. So if my DU, for example, was, let's say it's 0.75, and I need to apply 1 inch of water to this low quarter so that I can adequately irrigate the entire field, then I've got to say 1 inch divided by 0.75, and I think that's, I've got to apply 1.5 inches of water. And I probably didn't do that math right. Maybe it's 1.33 inches. But anyway, that's how much we have to adjust the amount of water we apply in order to over apply water everywhere in order to adequately irrigate the low quarter. So we cannot be efficient with our irrigation system if we are not uniform. So uniformity is very important. Some systems like this with surface irrigation system, most of the water losses are to deep percolation, because if we're using surface irrigation where the water is flowing across this surface and then runs off the bottom of the field, we go and look at the water running off the bottom of the field and oh man, that's water wasted. We get all concerned about it. But where most of the water is lost is actually deep percolation. because we've got water infiltrating at the top of the field for many hours before the bottom of the field gets any. And so this forces us to have water losses to deep percolation with these surface irrigation systems in order to adequately irrigate the bottom of these fields. So, but again, whether we should be concerned about that depends on basically the hydrology of that area, how much water we have at that particular time, and whether these deep percolation water losses are recoverable eventually, and whether they might even cause problems where they build up the water table and kind of drown out your crops. So again, we're talking about where do the water losses go. Sprinkle irrigation. With surface irrigation, most of the water losses is runoff and deep percolation, very little evaporation. So these surface irrigation, the losses from surface irrigation, large percentages of those losses are eventually recoverable depending on that particular drainage system. However, water losses from sprinkle irrigation systems, almost none of it is recoverable. The only water losses, so we have a runoff from sprinkle irrigation sometimes, but usually we don't. If we have runoff from sprinkle irrigation systems, then it's not being operated properly. And then if we also have unavoidable water losses to deep percolation because we don't have a perfectly uniform system, just like with surface irrigation, but we have these very large water losses to evaporation. With drip irrigation systems, it's kind of the best of everything because we have very little soil surface evaporation, no water losses to evaporation from water loss coming off the wet leaves. The only water losses that are unavoidable is because, let's say, we don't have perfectly uniform water coming out of each one of these drip emitters, and then in order to adequately irrigate every single one of them, we've got to over irrigate a little bit on these other ones. But again, we even have less water evaporation, very little, because not only do we have dry leaves, but we also are not even wetting the entire surface of the soil. So these areas of the soil that are dry, we don't have water evaporation. So with drip irrigation, we can become very efficient, especially with a drip irrigation system that applies a uniform amount of water out of every drip emitter. So again, let's talk about, we have leaks. Those are water losses, but maybe some of those water losses, it causes poor uniformity, right? And then, so that water is lost to the farmer. And again, he's over applying a ton of water right here in order to run this sprinkler in order to adequately irrigate the whole area. But some of those water losses, if you think big picture, again, drainage basin picture, some of those water losses are recoverable. However, forever losses, there's sprinklers operating, and especially on windy days, you can see this water just blowing away. You can see water droplets. You can see this light haze here. Those are water droplets. Once it gets converted to water vapor, which is where the majority of this water ends up, you cannot see it. So again, water vapor is invisible. We don't see that water loss. Out of sight, is out of mind. So the largest sources of water losses from irrigation systems are deep percolation and water vapor evaporation, and both of those we can't see. And so people don't think about it, but those they're huge. And so those are forever losses. And again, water losses from these systems. The more time that it spends flying through the air and the greater amount of air that it's exposed to, and the smaller the droplets, the more water losses you're going to have to evaporation. So with that, we can try to pick which irrigation systems we should be pushing, which irrigation systems are better than others. And so what we're going to try to do is say, okay, this is what the irrigation efficiency of these different systems are, but with the caveat that irrigation efficiency really depends on a lot of things. the operation, which is the timing, whether they turned the water on at the right time and applied the right amount of water, the pivot speed, the frequency of irrigation, where more frequent irrigation systems, the more frequently you wet the soil of the soil surface and the plant leaves, then the greater percentage of your water loss that's going to be lost to evaporation. It's also, it depends on our irrigation system design, nozzle sizes, pressure differences throughout the system, whether we can uniformly apply water with that system, the maintenance of the irrigation system, whether we're fixing leaks, the weather, wind speed, and vapor pressure deficit. Vapor pressure deficit is a fancy way to say aridity, you know, how hot and dry the air is, how much space there is in the air to hold water, additional water vapor. And then the wind speed are very, you know, that can really affect your irrigation efficiency, especially with sprinkler irrigation systems. Flow rates onto the field, especially with surface irrigation systems, getting the right flow rate so that it makes it across the field in a fairly short amount of time, but then you don't have too much runoff. Field and soil properties like the slope, the infiltration rate, the water holding capacities. So basically, irrigation efficiency is not one number. It varies from field to field and even throughout the day as the weather changes. Day-night differences are very visible, and we can see that. However, here's the numbers that we put together. Here's for these different irrigation systems. The irrigation efficiencies here. This is a literature review where I looked at all the literature I could find about the irrigation efficiencies of these different systems, and then tried to put together an idea of where the losses. So let's say this is 75% water losses. Where do those water losses go? So some of it is the deep percolation, and most of those water losses from sprinklers are to wind drift and evaporation, because this matters when we think about things as a whole, as a base on a basin scale and on a state scale. So how do we measure irrigation efficiency? We can use it with catch cans. Basically, we measure the amount of water that's coming out of the nozzles, how fast this particular system is running, or how long those sprinklers are on. We can calculate how much water should have made it to the ground, the depth of water, and then we measure the actual depth of water caught in those catch cans, and then there's a lot of water missing. So we say, okay, that water was lost to wind drift and evaporation. There's nowhere else it could have gone. We can also use these drainage lysimeters where we basically fill a tank full of soil, we bury it level with the soil surface, and then we capture all of the deep percolation water losses in order to do a soil water balance. So we can use this sort of a method. Here, they're doing flow rate measurements from particular sprinkler nozzles so that we can measure the flow rate versus how much water is actually caught on the soil surface. So here's some interesting things that we found. You know, basically, here's the range. So you can see day-night differences, first of all. So this is the high, here's the low, here's the median that we found for these irrigation water losses during the day. Here it is during the nighttime, and you can see both that there's a range in those numbers, as well as, you know, there's definitely day-night differences. And the day-night, you know, it doesn't really matter that much that the sun's shining. It matters more what the wind speed is and what that vapor pressure deficit is. And that vapor pressure deficit is strongly a function of the temperature. And there it is throughout the season. We took here's wind speed and vapor pressure deficit, you know, on this scale, the bars right here, and then this chart right here. This is the water application efficiency difference between a sprinkler irrigation system where it's really high off the ground and one that's really close to the ground. And what you can see there is that it's strongly, so May, June, July, August, there's a huge benefit to trying to avoid those wind drift and evaporation losses during the middle of the summer. And so that changes over time as well. So here we took all these different irrigation systems and then we sorted. So this is the fraction of the water that is lost. So as a decimal, or percent as a decimal, to from that particular irrigation system, and then we rank them. So surface drip or subsurface drip, where you bury the drip with tape, that's about as efficient as you can be, and it goes all the way up to wild flood. Wild flood is where you just basically dam up a creek and then you just run it out onto a field. Usually they don't do anything, they don't even level the field. They just it just kind of runs out there and they just do the best that they can. And then these systems this way. So this is the total, the blue is, these are the forever losses. So in other words, those are the losses to wind drift and evaporation. Or, so just to kind of bracket this, we said, okay, about half of the deep percolation losses are eventually recoverable, and about half of the runoff losses are eventually recoverable. So whether that particular assumption applies depends on the particular drainage basin, maybe even the particular field, the irrigation district, you know, what they do with the runoff water, etc. What we definitely want to do is limit these forever losses. And so if we instead rank it based on these forever losses, you can see the blue one. So this is the same information. Some interesting things come out. First of all, any sort of drip irrigation system is definitely very efficient because the wind drift and evaporation losses are very tiny, negligible. Also, because we're applying water directly to the soil, we can usually limit the water losses to evaporation from the soil surface as well. And then the other thing that's interesting is that surface irrigation isn't always the enemy. So this is basin irrigation right here, a level basin. Here's a border irrigation system. Here's a contour border. Here's furrow irrigation. If we look at, because they have a lot of water losses, but their water losses, some of them might be eventually recoverable. Whereas the water losses to sprinkle irrigation is almost always permanent and forever. So with that, some of the systems that we definitely should avoid is the pivot, you know, the linear, the sprinklers that are operating on the top of the pipe, the high impact sprinkler, you know, going on top of the pipe. Those have about 40% of the water. It doesn't even make it to the ground. And so those are definitely lost. Big guns, the same thing. We have a huge amount of water loss from big guns. Not only that, big guns, because they're so affected by the wind speed and direction, the uniformity on them is also tends to not be great. Hand lines and wheel lines. I've seen some programs where people are paying or incentivizing people to convert from furrow irrigation to hand lines and wheel lines. Maybe that's not the best idea based on this. You know, maybe that instead of those water losses being lost to, you know, building up our water table in these areas of the state where it's really dry, and we need that water in the water table to recharge because so many people are pumping it out and drinking it at home and or using it later. Maybe it's better to leave it in surface irrigation systems and avoid some of these other systems. Also, big guns on the end of pivots. We've done lots of evaluations. The big gun that operates on the end of the pivot, the irrigation efficiency is bad, the uniformity is bad. Those are not our friend. And so the other thing too, so look at this as a pivot, right? So we have, so just let's convert people to pivot. Well, it depends on how the sprinklers are set up. It matters a lot. So we have the pivot or linear where the sprinkler is operating on the top of the pipe. There's the pivot or linear where we've got the goosenecks and we have a mid-elevation spray. And then we have the pivot or linear where it's operating with LEPA or LESA, where the drops are right next to the ground and operating way down there. There's a huge difference between the way that those systems operate. So in general, what we want to do is get people to move their drops down and closer to the ground with those particular systems. And so I put together, okay, if you convert from one system to the other, you know, kind of whether you should see efficiency increases or decreases, and about how much based on those. Then I also did a thing where I wanted to compare different irrigation technologies. So some of the technologies, we'll just skip ahead really quick. The system conversions from one irrigation system to another, using irrigation scheduling, you know, how much water we could expect to save with those, and how much it costs, basically. And I assumed that all the costs is borne by the farmer. The irrigation automation, where we completely automate the irrigation system, variable rate irrigation, and low elevation spray, LESA and low energy precision application, mobile drip irrigation for center pivots, deficit irrigation, basically we try to save water by not applying as much water as the crops could use otherwise. And then different tillage to control runoff. So we dam or diker, or we do things so that water doesn't run off the surface of the field. And then conservation, no-till and strip-till. How much water can we expect to save? And then what are those technologies going to cost? So with that being said, I want to, how do we compare these? We want cost benefit ratio, right? So we want cost per acre per year. So I included the equipment costs for those different systems, the upfront labor costs for installing, including management. I have a management labor rate and then you know, a worker labor rate. Weekly recurring costs throughout the system. We made some assumptions based on those. Annual recurring costs, and then the percent water savings, which were possible, which we assumed as a percent. And then what we've tried to do is the cost per acre inch conserved per year, and we want that to be as low as possible. Basically, which technology should we focus on or push that's going to give them the biggest bang for the buck, the lowest cost per water conserved. Again, with irrigation efficiency, we have the same problems with cost estimates. We need cost and benefit estimates to require, you know, to make decisions. However, costs are obviously fickle. They move daily. They change all the time. However, depends on equipment costs, interest rates, wage rates, and again, irrigation efficiency depends. But I wanted to do something anyway to try to get an idea of what those actual costs were, and to kind of bracket which technologies are going to give us the biggest bang for the buck. You know, so we did this big analysis of those. So what we looked at soil moisture sensors, installing and using these, whether you buy them yourself and you own them, and then you install and monitor that over time, or you rent a service. Basically, you hire someone to come and install them and set it up, and then they charge you a certain fee per year, but they actually own the hardware. I wanted to compare ET-based irrigation scheduling methods, where we use either this, what Nicole just talked about, which is the ET, the weather stations, and then we combine that with this irrigation scheduler mobile model. There's also very simple models that we can do based on long-term historical data in the soil water holding capacity that we can use. These are simple paper and pencil based models based on average ET. And then I also looked at irrigation automation. So with irrigation automation, this is the same as basically perfect irrigation scheduling. We have the system that's set up that either uses some sort of data, either from ET or from a weather network or from a soil moisture sensor that's in the field, and it basically turns the water on and off automatically. Some notes on this is that we can do this and have been able to do it for many years, probably 20 or 30 years. This has been possible. However, it's not possible, it's not common, and people don't do it because of liability concerns for companies. They're just not willing to take this kind of risk, which is, I set up a pivot on a 120 acres of potatoes, and the system malfunctions, or they say, oh, you overwatered or underwatered, and therefore, my potatoes have black heart. They just, and then, here's your, $600,000 bill. They just want to pass on that. Liability concerns. Also, it also requires on-demand water, which for the flow rates that most irrigation systems use is not easy to do. Just being able to turn something on that's 1,000 gallons a minute and then turn it off at will usually causes problems for other people upstream or downstream. And also the required, you have to basically calibrate all of them, and it requires an individual system design and calibration. So big companies, big corporate firms do this often, but individual farmers don't, because it's expensive. And then some other things is high impact sprinklers on top of the pipe. We have increasing wind speed. The reason we put wind machines or windmills on top of really big towers is because the wind speed is higher up there. So we have this wind shear, it's called. We have the higher, as you go up, we have higher wind speed. And so we have spray losses of 30 to 40%. Here we have spray losses of 10 to 20%. And here, when we move it all the way down into the canopy, in some cases, the spray losses are very, very small. The wind speed down here is 0. And we're learning that operating the sprinklers below the top of the canopy is really not that big of a deal. It's possible. It requires kind of the conversion of your thinking on an operation of how that works. So that's LESA, low elevation spray. This is called low energy precision application, where it dribbles basically right onto the surface of the soil. This almost always requires some sort of conservation tillage method where to limit the runoff of the system, because it almost always applies water too fast for the soil to take it up. But in this particular type of system, we're leaving this soil dry, so we're limiting evaporation. And with this particular setup where there's dam or dikers, you can apply up to 1 inch of water at a time without any problem. So there's a lot of water savings possible with changing the operation of these semi pivots. So here we have MESA in the background. You can see the wind drift and evaporation loss. We have LESA in the foreground. And you can see, the air just goes clear here because there's no wind drift and evaporation losses. The problem with this type of a system is you're applying the same amount of water in a smaller distance or a smaller amount of time. So your application rate here is higher than it is here. And so it tends to have more problems with ponding and runoff than you do with this type of a system. So we basically tell people, hey, if you don't have problems with ponding and runoff on your field, please consider this. If you do have problems with ponding and runoff, you can speed your pivot up or something, but if that still causes you problems, then this is probably not going to be for you. There's mobile drip irrigation that we looked at as well, which is basically, it's a center pivot that, or a linear move system that drags drip tubing through the field, this is possible. It requires lots of very clean water, because any small bit of garbage that's in the water is going to plug the system, and then once it's plugged, it's really hard to unplug. You basically have to throw it away. But we can do this, but whether it's cost effective or not, with this system, you tend to not have the runoff problems that you do with this type of a system, because you're applying the water over a very long distance that's behind this machine. And then we look at deficit irrigation. So this is a generalized yield versus applied water or evapotranspiration. So the more water the crop uses, we get better and better and better yield, but it reaches a maximum, and that maximum depends on solar radiation, maybe fertilizer, maybe pest or other problems, the length of the season, etc. However, the amount, as we apply more water, we get the separation between our total yield and the amount of applied water, and then at some point it decreases. So we can usually save this water by coming down, by applying a little bit less water, and we don't have a comparative loss in yield. Let's say we use 20% less water, we come over here and we only have maybe a 5% loss in yield. So we can save a lot of water, but we have yield loss. And so we wanted to compare those. And then tillage to increase the soil surface water storage. Here's this particular system, which uses furrow dikes. This is confusingly, they also call this a dammer diker, but it basically just stabs holes in the soil, and then it increases the soil surface water storage. So you fill this water, you fill this with, you apply a lot of water with your irrigation system, and it fills these little holes with water, and it doesn't allow that water to run off, and it's got to sit there and infiltrate. Also wanted to compare variable speed irrigation systems with variable zone irrigation systems, variable rate irrigation, and how much water we can expect to save with those particular systems. They are particularly applicable to some areas where they've got basically these non-irrigated spots in the field where they can't crop because it's either rocky or ponded water or whatever. And as the best farmland gets paved over and they put parking lots and stuff there, then farming gets pushed more and more onto this type of marginal ground, and then so we're going to see more and more of this. However, the bottom line with variable rate irrigation system based on the soils, so if we have different soils with different water holding capacities in our field, let's say we have one area of the field that has a really deep and a silt loam soil, and then we have some areas of the field that are a shallow and sandy soil, ET, or the amount of water that's used by the crop, is the same, or the amount of water that the crop needs does not depend on the soil's water holding capacity. Therefore, in general, if we manage the entire field so that this shallow sandy soil doesn't run out of water, and we're not applying more water than this soil can hold, then the rest of these other parts of the field are going to be fine. Which means that just because we have different water holding capacities in the field, it doesn't mean that there's water savings available from variable rate irrigation due to variable soils. Where you can save water is if you have large in-season rainfall events. So basically, we irrigate, let's say we have all these soils in our field, we irrigate this shallow sand so that it doesn't have water stress, but we leave the water off to these soils and we allow it to deplete. down to the point where we're going to begin to see water stress, and then we start irrigating, we're saving space in the soil in these soils that if it rains and refills that, we can take advantage of that rainfall. Whereas in these soils, we can't take advantage of that rainfall. That rainfall will be lost to deep percolation. So this is where you can theoretically take advantage of variable rate irrigation to conserve, to save water, to use less water, but it depends on large in-season rainfall events and highly variable soils, which is not very common. I also want to talk about, compare the no-till versus strip-till, and whether leaving this trash on the soil surface is beneficial, how much water it can basically save. So this is the bottom line. The amount of water that we could save for the different technologies, and here is the kind of cost per benefit. So some of these technologies, like deficit irrigation, if you can keep the water, so if someone can deficit irrigate, save that water, and then irrigate other acres instead, they can make money. And so farmers are going to do this. In fact, Oregon allows growers in some areas of the state to do this, where they said, okay, you have this much land, you don't have water rights for all of it. We're just going to give you a set amount of water. How you use that is up to you. We don't care. And it's not tied to certain acreage. That grower can make money, and they do this where they are very conservative. They deficit irrigate many of their acres. They plan their crop mix very carefully so that they can get the maximum return for the water that they use, and they make money doing this. They're happy to do this. However, if you say, okay, we want you to deficit irrigate, but that water goes back to the state, then the grower loses money on that particular scenario. Deficit irrigation without water spreading, it costs them, about $8 per acre for every acre inch that they $8 for about every acre inch that they're able to conserve this. So in other words, growers are not going to be willing to do this. There's conservation tillage. Basically, growers can also make money because they're saving money, because they're not having to, that's with this particular scenario, they do less tillage, which saves tractor time, tractor wear and tear, diesel, driver time, and so they're not using as much and spending as much, and they're saving water with that. So all the rest of these technologies cost the grower a little bit of money. LESA is probably the biggest bang for the buck. ET-based irrigation scheduling, also very inexpensive to do because it's basically free. The cost there is just basically their additional time and attention that I actually placed a value on, which I think is fair. The mobile drip irrigation, that they can save a lot of water with that, but it's kind of expensive. And then soil moisture monitoring, where they buy and own that, versus soil moisture monitoring where they rent. It's a little bit cheaper. It's just a little bit more stress in their life and a little bit more things to learn and manage. Tillage to reduce runoff, which is a dam or diker. This is irrigation automation, deficit irrigation without water spreading, variable speed irrigation, and then variable zone irrigation. Variable zone irrigation, which is this variable rate irrigation system, which I basically set up for center pivots. Very expensive, and you can't save very much water with it. Again, I had to make some assumptions, so those numbers can vary quite a bit. So that's all I had. I'm about out of time, but I'm happy to answer questions.
Great, thank you so much. That's some great information, Troy, I'll remind folks, please type any questions you may have into that question box. You can also raise your hand. I can unmute you and you can ask it directly. So perhaps while folks are putting those questions in the question box, Eric, if you have any questions that you would like to get us started with, that would be great.
Sure, thanks, Nicole. Troy, I was curious in terms of, we have quite a few dairies in the state and so forth, and wondering, have you ever looked at running separated dairy, liquid dairy manure through any of these systems?
Yeah, so dairies are really different. So their objective is the beneficial use of their water is to move those slurries, and at some point they have more water than they need, and so in some cases it's beneficial for them to waste water. We consider it waste, but basically increase their evaporation losses, and so to be as inefficient with the water as possible, because they don't want to apply more water than the soil needs, but they need the water to move those soluble and insoluble solids away from the dairy system. So I have empathy for that need. That is a very real need, and that's a beneficial use of that water. We use water for the same purpose. We use it to move water and waste out of our houses. So
yeah, it's just interesting, like some of these systems, like the LESA or LEPA acronyms, they're wondering if dairy manure can get separated fine enough to not cause problems with those units.
Yeah. So
I think it's possible.
Those systems are they use smaller nozzles, because when there's more sprinklers, and those LEPA systems require more sprinklers, you have less water coming out of each sprinkler, which means a smaller nozzle, which means it gets plugged with smaller bits of garbage, which you can either filter it out, which that's not the point. The whole point of using it in dairy systems is to move those away and then spread it out onto the field. So again, that's a different scenario where they're using the water to move those solids onto the field. Big guns, actually, because you have big nozzles, and then they can throw that water out, and you can pass small rodents through those nozzles. Are really big.
Yeah. No, great, thank you.
Yeah.
Nicole, do you have any questions in the chat box?
Nothing coming in the chat box. It might be a little late in the day for people. Oh, here we go. Two just came through. The first one, are these sheets and formulas available on WSU's website to show producers your cost benefit ratio information?
Yeah, not yet, but I will do that soon. I'm happy to share my my presentation with Nicole and Eric, or whoever would like, and then you're welcome to use that in the meantime. Yeah, but I'll try to put it up. We've got a website, irrigation.wsu.edu, and you can go there and get a lot of this information. Usually it takes a while for us to go through the whole publication process, but what I've been doing is I just publish it in the meantime on that website, and then as we go through and get it cleaned up and looking pretty, then I replace it with those better versions of those publications. So.
Okay. Thanks, Troy. And I will say that website, there's a lot of good information. You can access it through the AgWeatherNet function, or directly as you can even just Google WSU irrigation. You guys have some great content there.
Yeah.
Another question we've got here, Question is the technology for variable zone irrigation systems robust enough that you think it would be appropriate for animal waste slurry applications where there are water courses and associated setback areas within the pivot area?
Yeah, the answer is yes. The technology is mature with that variable rate irrigation, variable zone irrigation systems. And that would be a good application of those actually is for waste disposal. And then if you have different amounts of waste that you can apply to different areas of the field for whatever reason, you know, soil samples, and you say, okay, this area is low and this area is high, and so we're going to use, again, this system as a variable rate fertilizer spreader, basically. Yeah, it would work for that. Like I said, the technology is mature. Reinke Valley and who's the other one? Zematic. They all have off-the-shelf systems that work. They've been tested. We've looked at them. They apply water uniformly, and they apply the amount that they say they're going to apply to the different areas. Of course, the difference in the zones is limited by the overlap of those sprinklers, but it's good. It works.
Great.
That was a
Thank you,
great
Troy.
question.
Yeah, there's no others in the chat box. I don't know if you have any additional ones, Eric.
You know, I had just one more where I got a little bit fuzzy thinking about the companies that, is it the companies that provide the monitoring equipment for irrigation scheduling? They're worried about the liability if they, on crops, if they were to cause a problem, like in that potato crop example you gave. How does that all come together again?
So what I was talking about that was with irrigation automation, where they are basically making the decision as when to turn the water on and off. The irrigation companies that do like soil moisture monitoring, they don't have those same compunctions. Anytime that you can give growers information, and as long as they have to make those decisions, then they can kind of separate themselves from that liability.
Sure.
I think irrigation automation, a potential for that is basically to set it up such that it says, hey, we're going to turn this system on unless you tell us not to. But still, they give all that information to the grower and allow him to at least intervene. There's ways to set it up to kind of separate, still take advantage of, you know, the best science and technology to do irrigation automation, but to limit the company's liability. It still requires, every system has to be kind of calibrated no matter what. You've got it, because there's so much variation in soil moisture sensors. ET is definitely not perfect. Lots of the systems, there's just a lot of inherent variability in the way that the particular grower wants to manage his field, when they harvest, when they wanted to experience water stress, if at all. That all has to kind of go into that system, but it can be done, I think.
Well, thank you.
Sure. So with the irrigation scheduler mobile model, I just want to go back and talk about that briefly. It's basically an app that people can use on their phones. It automatically brings in the irrigation estimate, the ET, the water use estimate from the nearest weather station, or whichever weather station you pick. And it adds measured rainfall events in there, and it gives you an estimate of how much space you have in the soil for additional water application. It lets you know about when you're going to start to experience water stress. It's a great tool. We tried to make it simple and user-friendly. To set it up, all you have to do is choose your weather station, name your field, and pick your crop, and then give an estimate of what your soil texture is, whether it's silt loam or clay loam or whatever. And that will get you set up with a bunch of defaults for crop coefficients, soil water holding capacities. It puts all that information in there for you. But again, it shows you what information is there, it used, and you're welcome to change that. In fact, I encourage you to change those, especially the season dates. Those are wild guesses. We all know planting and harvest dates change a lot season to season. And so please go in and look at those and sanitize them if possible.
What was the name of that program again?
Irrigation Scheduler Mobile,
Okay.
and you can find it on the iTunes or on the Android, and download it. And hopefully you can find the weather station that you want to use.
Great. Well, we're just kind of hitting the end of our hour. Anything else you want to add, Troy or Eric?
I don't have any more questions at this time.
Okay.
Yeah.
Well, thank you so much, Troy, for taking the time to be with us today. We're all giving a round of applause from our quiet spaces.
Yeah.